All right, this is Mr. Hebner. During the 2020 pandemic, we're working on electrochemical cells, more specifically Voltaic cells, also known as galvanic cells. All right, so let's see. Oh, that's for chemistry. Where is it? All right. Electrochemistry is the study of the relationship between chemical and electrical work. Alright, and there's two big branches of electrochemistry. One, voltaic cells, which is like your typical battery, and the other is electrolytic cells, which is the reverse of how a battery operates. We'll talk about those. So these are systems consisting of electrodes that dip into an electrolyte. And anybody know what an electrolyte is?
Gatorade.
Well, that's an example of electrolyte. So it's an aqueous solution of ions. So it's a mixture of ions. So there's two electrodes which represent the two half reactions in a redox reaction. And the chemical reaction redox either uses or produces electricity, so a flow of electrons. So yeah, we got half reactions. One is going to be reduction, the other is going to be oxidation. And when you put them together, you got a current as long as there's a salt bridge. And we'll talk about all of that. So voltaic cell, let's get the definitions of the two main branches. An electrochemical cell in which a spontaneous reaction generates an electric current which is measured in volts. Alright, key is spontaneous. So if it's non-spontaneous, then it's useless. It's not going to work. It's not going to generate a current. But you could put a current into it, like plug it into an outlet. But then it would be an electrolytic cell because you'd make a non-spontaneous reaction, then react because you're actually adding a current to it. So the confusing thing about electrochemistry is you learn about voltaic cells, and then you got to do the opposite for electrolytic cells, and then know the difference between the two and go back and forth. And then IB has a bunch of specific electrolytic cell examples that they want you to know, which makes it tough. So an electrochemical cell for electrolytic cell in which an outside electric current drives an otherwise non-spontaneous Alright, so it's useful for isolating important elements. So you can do electroplating, take stainless steel silverware, and you can coat it with gold using an electrolytic cell process. Or galvanized steel nails, you can coat stainless steel. Actually, I'm not sure, I don't think it's stainless steel, I think it's just iron. Coat it with zinc to get a galvanized nail. And zinc's not going to oxidize and turn it into rusty as much, so it's good for outdoor decks and all that stuff. And they cost more. So. All right. So we're just going to focus on voltaic cells, and not next week, but the following week we'll get into electrolytic cell. Nice thing about getting rid of paper 3 is we can really kind of go slowly with this unit. Otherwise, this unit we, under the block schedule, cram into barely 2 weeks and don't really know it that well. So hopefully we'll do well on the redox questions on the IB test in May. So it consists of 2 half cells, a metal strip, an electrode that dips into a solution of its metal. Usually are made up of magnesium, zinc, iron, copper. I think there's a nice little picture. I'll draw a little picture too. So we got a metal strip, and then a solution of ions. And you got a voltmeter, just kind of measuring the volts. But then you have to have a salt bridge to make the current flow. Otherwise, you're going to have a buildup of charge, and it's going to be a moot point, not do anything, unless you have a salt bridge to release that charge and complete the circuit. All right. So half cells generate electrode potentials. So what's an electrode potential? Charge separation between the metal and its ions in solution. And here's an example. We got zinc atoms will form ions, which is zinc 2 plus. By releasing electrons that make the surface of the metal negatively charged. And at the same time, ions in solution gain electrons to form zinc, thus equilibrium exists as zinc 2 plus aqueous plus 2 electrons form zinc solid. So, and there's a back and forth. Here's the equilibrium. And depending upon the value of the electrode potential will determine whether it'll be favored to the left or to the right. That takes us to the next page. So we got 15 minutes. All right, so here's kind of a picture of what's going on. You got zinc atoms are losing electrons and thus forming zinc 2 plus over here. Or you could say that zinc atoms are gaining electrons and forming zinc solid. So you got equilibrium. right. So the size of the half-cell electrode potential depends on the reactivity of the metal and the position of the equilibrium reaction. So for example, we got copper is less reactive metal. We know that from the activity series right here, and go all the way down. Copper is towards the bottom, so it's not very reactive, which means it's going to be reduced as opposed to oxidized. It acts as a very good, it's going to be reduced. So what type of agent would you call that? Oxidizing agent, you got it. Alright, so copper is less reactive metal according to the activity series, therefore copper has less of a tendency to lose electrons. It's going to gain them. This means that the equilibrium reaction for copper 2 plus lies further to the right. Just going to rewrite that there. Left and right. Oh, there we go. Yeah. So it's not going to be oxidized as much, so therefore equilibrium is going to be a solid. It's most likely going to be the substance that precipitates out. So which direction will the equilibrium reaction favor for magnesium solid in a magnesium sulfate solution? Here's the reaction. Is it going to oxidize or is it going to be reduced? So we're looking at magnesium is all the way right here. It's actually in the upper half. So if it's in the upper half, it most likely oxidizes. You got it. So it's a good reducing agent. So if it oxidizes, it's probably going to favor to the left, equilibrium. All right. Two connected half cells make a voltaic cell. So once you take like an oxidation reaction of magnesium, connect it to a reduction reaction of copper, and you connect them with a salt bridge, you got a voltaic cell. And voltaic cells must have the following connections between half reactions: electrical wire connected and a salt bridge. So without a salt bridge, no voltage will be generated. It'll just build up and you won't have a complete circuit. Alright. So the direction of electron flow and voltage generated is determined by the difference in the reducing strength of the two metals, which in most cases can be judged by the position of the metals on the reactivity series. Example, the voltage produced by a zinc and copper cell is less than that of a zinc and silver cell because there is greater difference in electrode potentials of zinc and silver than zinc and copper. So looking at that, we got zinc and copper. Copper's right here, and zinc's right here. So we got somewhat of a difference, but then looking at silver and zinc, silver is further down, so there's a greater difference. So the voltage produced by a zinc and copper cell would be less because the difference between them on the activity series is different. So silver is much better at being reduced than copper. Alright, this is something that you're going to have to memorize, and then it kind of flip-flops when you do electrolysis. So anode is the electrode at which oxidation occurs. Electrons are given up by the reducing agent. Alright, and you can remember it with ANO. A stands for anode, N stands for negatively charged, and O stands for oxidation. Ano, anode. And then cathode is the electrode at which, what do you think, reduction occurs. Electrons enter the cell. And CPR is the mnemonic device. C stands for cathode. What would P stand for?
Positive charge.
Positive charge, you got it. And R would be reduction. There it is. So NO-CPR, anode negatively charged oxidation, CPR, cathode positively charged reduction. Oh, and then here's the electrons flow from anode to cathode. You can think of it as fat cat. So flow, from anode to cathode, which would be negative to positive. All right, just a little bit of time left. Here's a diagram that I kind of drew at the beginning, showing your salt bridge, your voltmeter connection, your two metals, and your solutions. So, and based off of the electrode potential and the difference, is going to determine how high your volt is. And in your data packet, we'll work on this next week, Monday. We'll instead of notes, we'll do like practice/notes on it, and we'll look in our data booklet. Then we'll also go over textbook questions, so I'll extend the due date on the Zoom call. So, yeah.
I know you said there isn't an online version of the Pearson, but is there one of the Zoom dolls that I could start the question?
There is one of the Pearson, but not of the Zoom doll, unfortunately. They want money. So.
Nothing to do during my study.
You could borrow. Actually, I don't have one. You can borrow my one as long as you return it. Oh yeah, one more thing. Shorthand writing of the reaction in a voltaic cell. So you got zinc solid and zinc 2 plus. You have to separate the what's happening within the oxidation half reaction cell with a line, and then you have the other cell. You separate the two things with a line, the entities that are being reduced or oxidized, and then you separate the two half reactions with a double line. And you always have your electrodes on either end. Yeah. Yeah. So yeah, electrodes have to be on either end. And if you forget that, these are all the words that basically summarize what I said. So the anode is written first. Actually, yeah, you might want to write anode first. Anode. Anode, is that negatively charged or positively charged?
Negative.
Negative. And is it oxidation or reduction? Oxidation. You got it. To the left of the cathode, reduction half cell. A single vertical line separating them. Double vertical line, half cell represents boundary on either side of the cell bridge. All right. And the electrons flow which direction? Anode to cathode. Fat cat. There it is. All right. I will be done with that. I'll see you later. See you in 2021 without the mask. All right.